I'm Shinsuke Imada from Nagoya University. Today, I would like to discuss next generation solar space mission, Solar CUVST. Especially, I would like to concentrate on the topic of magnetic reconnection science with Solar C. I would like to start from why observing solar atmosphere is important. Because we can observe solar atmosphere in detail with high spatial resolution and high temporal resolution. We can understand elemental physical processes from solar observation. One of our science goal is understanding the solar atmosphere, which connect to the heliosphere via radiation, the solar wind, and coronal mass ejection and energetic particles, is essential for establishing the conditions for life and habitability in the solar system. There are three big issues for science roadmap of space agency, and the first is how the universe, matters, space is created and evolves. Second is how the solar system and life is created. Third is leading and innovation in space engineering technology. We can contribute the second one, how the solar system and life is created through the solar physics. How sun can affect our solar terrestrial or heliospheric environment. There are roughly two ways. One is steady phenomena such as radiation from solar atmosphere, solar wind, galactic cosmic ray modulation, and the other is transient phenomena such as flare, CME, solar energetic particles, and both of them can largely affect solar terrestrial or heliospheric environment. Let's introduce the history of Japanese sun observing spacecraft missions. The first one is Hinotori, which observes particle acceleration and plasma heating in solar flares. The second one is Yoko, which observed the particle acceleration and plasma heating in solar flares and general coronal activities. The third one is Hinode, which observes general solar activities of magnetized plasma. Then, what is the next? In June 2016, NASA, JAXA, and ESA chartered the Next Generation Solar Physics Mission Science Objectives team to study and report on the multilateral solar physics mission concept. 34 white papers have been submitted. After more discussion, 3 top-level science objectives have been decided. First one is the formation mechanism of the hot and dynamic outer atmosphere. Second one is mechanism of large-scale solar eruptions and foundation for prediction. The third one is mechanism driving the solar cycle and irradiance variations. Further, NGSPM SOT conclude that 3 types of observation are needed to clarify those top-level science objectives. Japanese solar community with US and Europe discussed what is the next mission. Then we decided Solar C mission. High-resolution corona transition region spectrograph to clarify the top-level science objectives, first one and second one. What are new scientific steps? In order to advance our understanding of the origin of the hot solar atmosphere and occurrence of the solar flares, the Solar CUVST mission concept tackles the scientific objectives by taking the following unique approaches. The first one is to seamlessly observe all the temperature regimes of the atmosphere from the chromosphere to the corona simultaneously. The second point is to resolve elemental structures of the solar atmosphere and track their changes with sufficient cadence. The last one is to obtain spectroscopic information on dynamics of elementary processes taking place in the solar atmosphere. I would like to show you the example of the spectroscopic observation. This is the example of Hinode ice observation. The horizontal axis shows the wavelengths and vertical axis shows the photons. You can see many spikes which correspond to the emission lines. Spectroscopic observation can observe many different emission lines which generally correspond to the different electron temperature. These images are the active region observation with different emission lines. The first one is iron 8, which is the coolest one. The last one is iron 16, which is the hottest one. Generally, the images of different emission lines shows the different structure because temperature are different. Let's move on to science objects of the Solar C UVST. The first object is understand how fundamental processes lead to the formation of the solar atmosphere and the solar wind. This is related to the famous solar physics program, coronal heating program. The temperature in solar corona is generally high up to a few megakelvin. How to heat the corona is a long-standing problem in solar physics. One plausible mechanism for coronal heating is small-scale unresolved reconnection heats the corona. Background coronal loop image is observed by Hinode EIS. You may understand we cannot spatially resolve the elemental coronal loop itself. Right figures are the example of small-scale heating event observed by several telescopes. Yoko has 3 arcsecond resolution and Hinode XRT has a 1.5 arcsecond resolution. Only brightening can be observed. We cannot find any reconnecting current sheet from this observation. On the other hand, if we go to high-C sound rocket observation, which is 0.3 arcsecond spatial resolution, we can see the reconnecting current sheet-like structure inside the coronal loop. This is one of the reasons why we believe 0.4 arcsecond spatial resolution is important. We can observe small reconnecting current sheet. Another important thing is the connection between the chromosphere and the corona. Hinode SOT found that the chromosphere is very dynamic. Because the spatial resolution is largely different, we cannot understand the connectivity between the chromosphere and the corona. Therefore, we believe that observing all the temperature regime of the atmosphere from the chromosphere to the corona simultaneously with high spatial resolution is crucial. The second science target is understand how the solar atmosphere becomes unstable, releasing the energy that drives solar flares and eruptions. In these days, flare process has been well studied and found that sometimes the flare trigger drives ideal MHD instability that causes magnetic reconnection. And sometimes the flare trigger drives the magnetic reconnection that causes ideal MHD instability. Magnetic reconnection and ideal MHD instability affect each other and causes a large flare. Understanding the relationship among them is important to understand the solar flare. Understanding the fast magnetic reconnection process is also an important topic for flare study. Reconnection region observation is crucial for the understanding. So we set these sub-objectives for flare study. Today I will discuss first one, probe plasma conditions and structures inside the reconnection region. To understand the fast magnetic reconnection process, it is crucial to probe plasma conditions and structures inside the reconnection region and clarify the role of shocks and magnetic islands in fast reconnection. These figures show the example of observation of magnetic reconnection associated with limb flare. If we compare large-scale structure, the left event seems to be Pechek-like reconnection, and right event seems to be plasmoid unstable type reconnection. However, because we cannot resolve the inside the sheet structure, which size is a few arcseconds, we cannot discuss the heating or acceleration process in the reconnection region. Therefore, we need sub-arcsecond resolution and 10-second temporal resolution with high dynamic range, plasma diagnostic capability, such as electron density, velocity, electron temperature, or ion temperature, or non-equilibrium ionization. I would like to mention what is a non-equilibrium ionization. If plasma heating occurs, then plasma starts to ionize along with this equation. Red arrow represents the ionization and blue shows the recombination. After some time, all red arrow and blue arrow become equal, which means reach to equilibrium state. Generally in solar corona, this equilibrium time is very short. Therefore, most people assume ionization equilibrium. However, magnetic reconnection process is also very fast process. So when we discuss magnetic reconnection, we should consider it. This is a time-dependent ionization in and around reconnection region. The reconnection outflow travels left-hand side to right-hand side with alpha velocity. Typical ionization timescale is a few 10 seconds, and alpha transit time is also a few 10 seconds. Thus, ionization proceeds along with the flow. Let's discuss one of the examples of the plasma diagnostic of reconnection region observed by Hinode eyes. Warren et al. 2018 discussed the electron temperature along the sheet structure above the post-flare loops. If you assume ionization equilibrium, then you can estimate electron temperature from the ratio between iron 24 and iron 23. Their results suggested that the plasma is gradually heated along the downstream of reconnection outflow. As I mentioned before, reconnection is highly dynamic phenomena, so we should consider time-dependent ionization. This is a result of reconnection region diagnostics considering non-equilibrium ionization. We assume density is 10 to 10 cc, outflow velocity is 1000 km per second, and 3 constant electron temperature. And the figure shows the model calculation and observation of ratio between iron 24 and iron 23. It seemed very consistent with constant electron temperature 25 megakelvin. Unfortunately, Hinode does not have many emission lines in high temperature range, so we cannot confirm electron density or other ionization population. Solar C can diagnose reconnection region more detail because wide wavelength coverage provides us more diagnostic capability. This is the summary of Solar C UVST, and Solar C UVST will be launched 2026 winter.